coffee line was quite long, which maybe says how everyone spent their last night. But I'm glad that you're able to join us here. And I want to acknowledge, if it hasn't already been acknowledged, right, the ordeal that it has been for some people to get here for the conference. I'm going to just do a quick check. How many people did it take more than 10 hours from when you left your home to when you arrived here? By show of hands. All right. Yeah, that's a good number of people. More than 5 hours. All right, more than 2 hours. Okay, and how many of you just lived downstairs and walked up? Okay, wonderful. So it looks like, 2/3 of everyone here, it took more than 5 hours, right? Which shows your commitment and shows your interest in the topics that we're discussing today. Especially want to thank our panelists who have volunteered and agreed to be a part of this really good conversation. I'm really excited to hear the discussion this morning as we talk about large loads and hydrogen, talking about the projections, talking about the technology, talking about the flexibility and some of the challenges as well. And so we'll get a wide range of opinions, I think, from the panel, which is what I believe we're all looking for, starting with a policy level type discussion, looking at some of the technology, the growth that we're thinking of, and then we'll round it off with a perspective from the system operator, right? How is this actually showing up when the rubber meets the road? What are the considerations? What are the challenges? What's the processes like? And so I have the wonderfully important job of introducing our speakers and then just getting out of the way and letting them take lead. And so we'll get started here with Dan Esposito, who is the director, is a senior policy analyst with energy innovation. Dan's topic is going to be how the clean hydrogen production tax credit will affect electrolyzer growth and flexibility. So please welcome Dan as we jump into this discussion. Thank you.
Testing, can you all hear me all right? Great. Well, thanks for the introduction. It's really great to be here. I'm going to be talking about the growth of the clean hydrogen industry, and specifically how a new federal tax credit is going to affect where we see electrolyzers and what type of load growth we would get from that technology. So I'm with Energy Innovation, which is a nonpartisan climate policy think tank. We provide objective research based on scientific assessments, and our goal is to identify the most effective economy-wide emissions reduction policies. I'm a senior policy analyst with our electricity program and lead our clean hydrogen work. So I'm going to be covering 5 things today. First is just how hydrogen production affects the grid. The second is a deeper dive into the Section 45V clean hydrogen production tax credit and how that would shape the industry's load growth over time. Third is how loose tax credit guidance for this rule could cause a lot of chaos and uncertainty for utilities. And then fourth, on the other hand, how stringent guidance could actually create a load that is beneficial to the grid by being highly flexible. And then I'll round everything out with a summary. So just a level set, almost all of the 10 million tons of hydrogen that we produce annually in the US comes from a process called steam methane reformation. This splits hydrogen molecules from methane, mostly by burning another stream of methane to generate heat. And that produces 10 kilograms of carbon dioxide equivalent per kilogram of hydrogen. And you can start cleaning up this process by attaching carbon capture equipment to it. That only gets you so far. So the only scalable way that we know today of making truly clean hydrogen is through a process called electrolysis, which splits hydrogen off from water molecules by using electricity. And this can produce anywhere from 0 to 50 kilograms of carbon dioxide equivalent per kilogram of hydrogen, with that dependent entirely on where you're getting your electricity. So why do we need hydrogen? Well, it's mostly going to be used to decarbonize things that can't be easily electrified. These 3 waves of end uses comes from the Department of Energy and where they envision it being used. So it's a lot of heavy industries, chemicals, aviation, commercial shipping, things of that nature. And I bring this up because this kind of helps clarify where you might expect to see hydrogen production, or at least transportation to those end uses. And second, these are really energy intensive industries. So we're going to need a ton of hydrogen to be able to decarbonize all these processes. So hydrogen wasn't really on the radar until a couple of years ago, and two federal laws have really accelerated its relevance. The first is the Infrastructure Investment and Jobs Act from 2021, and it sets aside $8 billion in federal funds for the creation of clean hydrogen hubs all across the country. The Department of Energy is still deciding where these hubs will be placed, but their purpose is to act as research and development for different ways of making hydrogen, using it, transporting it, and storing it. And as you can see from all the green on this map, these are places where states and cities are proposing to use electrolysis as their production method. But where we're going to see most hydrogen, or why we're going to see most hydrogen growth, comes from the Inflation Reduction Act, which has a Section 45V clean hydrogen production tax credit, and that's meant to really scale deployments. So this tax credit is structured by paying out on a dollars per kilogram of hydrogen produced basis, and you get more money if you reduce your upstream and production greenhouse gas emissions from that process. You can see that really high orange bar of $3 a kilogram being pretty tough to achieve. You need to reduce emissions by about 95% relative to steam methane reformation. And this is can't overstate how big of a subsidy this is in power market terms. $3 a kilogram is about $60 a megawatt hour. Plus you can sell the hydrogen. Competitive rates today are $1 per kilogram. So this is an $80 per megawatt hour value on the grid from electrolysis. So the US Treasury right now is thinking through how to design this credit. And the main question is, how do you measure the upstream emissions from the use of electricity and your electrolyzer? And that's going to really spell how this all plays out. So how much load growth are we talking about here? Well, these are the three goals set by the Department of Energy. The one closest to us, 2030, is 10 million metric tons of clean hydrogen production. If they meet this goal, it's not going to come entirely from electrolysis, but if it did, that would be 500 terawatt hours of load growth, which is about 12% of the load we had across the country in 2021. So the big question, well, two big questions, how much of this is going to materialize, but the bigger one for today is, what type of load is this going to be? And that is going to be answered by how Treasury sets these rules. So from a scientific perspective, the only way to actually meet that threshold for $3 a kilogram is to meet these three principles. So first is additionality, which is having your electrolyzer use new sources of clean electricity. Second is deliverability, which is making sure that that clean electricity is local and accounts for transmission line losses and congestion. And third would be time matching, which is ensuring your electrolyzer runs at the same time of clean electricity generation. And Treasury is considering how and whether and how to implement each of these three principles, and that's going to determine the amounts of load growth, the pace, the location, and the flexibility of all of that growth. So just going to introduce each of these principles in a little bit more depth. If you do not have an additionality requirement, then basically what you're going to do is build an electrolyzer connected to the power grid and claim the use of existing clean electricity by buying voluntary renewable energy credits, or maybe hooking up to an existing nuclear power plant. But in most hours all across the country, renewables and clean energy at large are producing as often as they can. So the actual impact to the grid is ramping up fossil fuels, which comes with emissions. I'm sure most of this crowd is familiar with dispatch curves, but basically if you add new load and you do not also add new supply, again, in most hours in most of the country, the impact is going to be calling on fossil fuel power plants to ramp up. When you account for these emissions and your estimates of the emissions intensity of hydrogen, then our analysis shows that you end up producing hydrogen with 2 to 4 times the emissions intensity of how we make it today through steam methane reformation. But more importantly for this discussion, you can be up to 100 times higher than the threshold for earning that $3 a kilogram tax credit. So the way you address this is by having an additionality requirement. This could mean building new clean energy, uprating a nuclear power plant, or using energy from renewables that would have otherwise been curtailed. For deliverability, if you don't have any sort of requirement in place, you might build your new clean energy in a place like West Texas and then site your electrolyzer in Houston, which would be logical on both accounts. But your clean energy might be displacing existing clean energy in a lot of hours due to congestion. So you might just be worsening the curtailment problem. And in Houston, you might be therefore causing fossil fuel power plants to ramp up in that area. And so depending on where you are in the country, this can really vary, but you're looking at, emissions as high as 17 kilograms of CO2 per kilogram of hydrogen, which is again, well above that credit threshold. So deliverability requires building these things locally and accounting for transmission, congestion, and line losses. And then lastly, we have time matching. If you build new local clean energy, but annually match its production with your electrolyzer's consumption, then in some hours, your electrolyzer is going to be consuming more than your clean energy produces, which will increase fossil fuels. And in other hours, you'll be producing more clean energy than you use and offsetting fossil fuels. So in the short run, the emissions impact is pretty modest, but often you're still outside that threshold. From an emissions impact, we're more worried about the long run risk here, which is that if you build a bunch of these annually matched systems, then you're going to end up displacing things that would have been built anyways. And then you're kind of right back where you started with a high emissions risk. So hourly time matching prevents this. It makes sure that you are only running your electrolyzer when clean energy is actually operating. So there's a lot of groups out there that are kind of fighting against one or more of these pillars, or at least how they're implemented. So if you didn't have an additionality requirement, you would be able to use power from today's existing nuclear power plants and hydropower, for example. If you didn't have deliverability, you would have a lot more ease in building electrolyzers anywhere in the country. And if you didn't have hourly time matching, then you could build projects like just overbuilding a bunch of solar and with your electrolyzers and not having to build cost optimized portfolios. So it's really going to be up to Treasury to decide how this all comes into play. And the reason those arguments are made against these pillars is because these groups claim they're either too difficult to implement or they're too expensive. And in our analysis, we found this not to be the case in either case there. So to implement these three pillars, all you really need are two products. One is very standard in the industry, a long-term power purchase agreement signed within a couple years of new clean energy coming online. And the other is hourly clean energy credits, which is just a more granular version of the clean energy credits that we already have today. These hourly versions are already available in much of the US, and they can be scaled up before 2026. For the economics, it's helpful to understand three different types of project configurations that you can have that comply with those three pillars. So the first is off-grid projects, where you just build new clean energy and electrolysis completely off the grid. You don't interact with your utility at all, and you would be wasting some energy, but you would probably be able to have your pick of lands and not have to deal with the interconnection queue. In the middle, we have export-only projects, where you have the same kind of co-location project, but you connect it to the grid, and you allow the one-way sale of excess clean energy to the power grid. This is clearly compliant with the three pillars that we were talking about. And you can monetize that excess energy as well. And then lastly, detached projects is kind of the goal. You want to be able to build clean energy in different places than you're building your electrolyzer. And to ensure that that's zero carbon, you need to follow those three pillars by doing those or having those two products that I talked about, the PPA and the hourly credits. So for these last two, the grid connected projects, how might they earn money? Well, you would want to overbuild your clean energy relative to the capacity of your electrolyzer, and that allows you to get a higher utilization rate, though you don't need 100% load factor. Your sweet spot is probably 60 to 80% or so. And then you can sell off excess generation, that's these gray bars, and make money that way. Or you can ramp down your electrolyzer entirely and sell all of that clean energy to the grid at a premium, which you would want to do when power prices are above about $80 a megawatt hour. And you can already see how that would be beneficial to the grid. So we modeled the economics of these export-only projects in West Texas, Houston, and Southwest Minnesota, and found them to all be highly profitable. These green dots are where you would probably be profitable from day one under the more stringent tax credit guidance. And we would expect this to expand from wind-rich regions to a lot more of the US as electrolyzer capacity costs fall. There's also, you don't have to take our word for it. Princeton did a meta-analysis of all public studies, including studies from some hydrogen renewable developers, and they all agree on this. Happy to share that around to anyone interested. So now let's get into the two possible worlds we might see depending on what Treasury does here. And these are kind of the boundaries with a lot of possibilities in between. Under loose tax credit guidance, where you don't follow any of these pillars, as a developer, you are going to build the cheapest hydrogen technology you can, so it probably won't be especially flexible. You will be incentivized to run it essentially around the clock, and you can buy voluntary renewable energy credits from existing plants on cents on the dollar these days. And you wouldn't really need to invest in storage or pipelines because you are running all the time, so you have that steady stream of hydrogen to your off-takers who probably desire that. The reason this is a problem is you're building a system that's entirely dependent of tax credits and will never be able to get off of them. So during the subsidy period, you can buy power anytime prices are at or below $80 a megawatt hour, and your off-taker is happy because you just send it directly to them. Once the subsidy expires, now the only way, with free equipment and transport everything, the only way you can make competitively priced hydrogen is by buying power at or below $20 a megawatt hour. So you're going to have a lot less supply all of a sudden. You won't have the kinds of pipelines or storage in place to smooth those gaps in production, and suddenly your entire business is in trouble. So for utilities, what that could mean is over the next 10 to 20 years, you see a bunch of new 24/7 loads coming online. And then either they might drop offline, which might not be a huge problem, actually. But the bigger risk here is that we've now propped up this industry and are concerned about what will happen to all the jobs and stranded assets. And so we extend the tax credits, indefinitely. And then you are just kind of extending this problem as well with all these new 24/7 loads. So pretty grim future possibility. If you have more stringent tax credit guidance that follows those three principles, then now you're incentivized to, anytime you build an electrolyzer, you're building at least enough clean energy, probably more to monetize or to get your load factor up. And you're building a lot more flexible units, including the balance of plants, the pumps and compressors and the business models that you have with your off-takers. And because you're not producing hydrogen all the time, you're probably building at least some hydrogen storage or pipelines to smooth gaps in production so that your off-taker always has what they need. So during the subsidy period, you might actually even see net load fall because you're building more renewables relative to your electrolyzer and you're time matching that consumption. And when the subsidy expires, everything is still set up for success because the electrolyzers now instead of being tied to new renewables, now they're just buying power at or below $20 a megawatt hour. They're set up for that flexibility. They have the storage and pipelines in place. Everybody's still happy. These projects continue to survive and grow. This is great for the grid because at very low power prices, you have suddenly many gigawatts of electrolyzers that are soaking up that excess renewable energy. And then when power prices rise, all of that renewable energy is made available to the grid to offset fossil fuels and generally keep the grid reliable. So it's a great base of flexible demand that as a utility or grid operator, you don't actually have to think too much about. It's going to operate on its own in a way that's beneficial to your system. So to summarize, in a world of loose tax credit guidance, you would have lots of inflexible 24/7 loads coming online all across the country. There's going to be a lot of uncertainty as to how much of this you have and how long it stays on your system. And again, it's very power hungry, overly subsidized. Under stringent guidance, you would have more renewables and loads come online. There's this long-term flexibility benefit that you can utilize to integrate renewables and keep your system reliable. And the reality is there's a ton of potential scenarios in between. We don't know exactly when Treasury is going to come out with these rules. It's kind of expected in August based on what the IRA requires, but that doesn't necessarily mean that's when it'll be released. And they might have, half-baked measures of all three principles, or, two strong principles and removing one of them. So there's a lot of potential in-betweens here, but I wanted to kind of give a sense of where the boundaries are of this load growth that you might expect to see. So thanks a lot for your time. If you're interested to hear more about our research, you can look up our paper here, but otherwise really looking forward to the questions and discussion later. And yeah, thanks again. Over to you, James.
Okay. All right, thank you so much, Dan, for that really engaging conversation. And I imagine there's going to be a lot of questions on the guidance. And if we're looking at decarbonization as a goal, whether we go with the more stringent or the loose guidance, right? And how that gets us to that eventual goal, either more renewables or is it more loads as we try and electrify the system. And so talking about that, right, we will turn over to Patrick, who is the Director of Energy Markets at Rondo. And Patrick's discussion here is going to be on heat batteries for industrial electrification as we look at one of the specific technologies as we're thinking about electrifying the system. So please welcome Patrick as he gives his discussion.
Well, good morning, and thank you, James. Thank you, everyone, for showing up this morning. Thank you for the opportunity to talk about Rondo and electrifying industrial loads. I think there's a lot of parallels here to what Dan just talked about, whether it's using electricity to make hydrogen or using electricity to electrify large industrial loads. There's a number of interesting, I think, parallels. The big difference is that in many cases, what we're working on doesn't hinge on a tax credit. Right now, we're finding cost-effective opportunities to begin deploying this technology. But at our core, we certainly don't want to be driving greenhouse gas emissions up. And many of our customers who are interested in electrifying loads are doing this for sustainability reasons, and they don't want to be swapping scope 2 emissions, reducing their scope 1 emissions, like reducing their natural gas burn on site and then increasing their scope 2 emissions. That's not what we're seeking to do. So eventually there might need to be some similar regulations in place, but like I said, right now we're beginning to see opportunities right now without a tax credit. So let's start by looking at what the big picture of industrial electrification can be. We all know that intermittent wind and solar now provide some of the lowest cost energy in history. For the last several years, unfortunately, we saw solar and wind PPA prices going up. And this is not what we at Rondo wanted to see, but with the Inflation Reduction Act, we're beginning to see that curve bend back down. For example, I'm working with a mining company in California. We're working with a large solar developer to design a solution for them, and we're seeing a solar PPA that could be as low as $22 per megawatt hour. It's a bit of a unicorn project. It has great solar irradiance. And some of the kickers on the tax credits that could get us up to the 50% investment tax credit. But either way, it's good to see that solar and wind PPA prices are coming back down. We all know that intermittent wind and solar is not as useful as base load. The grid needs more continuous and dispatchable resources. So do industrial customers. Most industrial customers in process heat, most of those processes are continuous. And so we're working on designing a solution that can convert intermittent wind and solar into consistent base load heat for industrial customers. When Rondo started off, we looked at the industrial electric thermal energy storage market, ETES. market. And using IEA data, you can see that total world energy use, about 36% is industrial. Of that 36%, nearly 3/4 is heat. So that's really the market that we're tackling. And if we did some rough estimates, how much storage would it take? How much installed storage would it take to really take intermittent resources like solar and wind and then turn it into 24/7 heat and steam? It would take, we estimated 41 terawatt hours and about 2 trillion of installed CapEx, assuming our cost of the system. Our system, we'll get into it in a minute, but it's essentially brick. Brick is fairly cheap compared to batteries. And so about 2 trillion of CapEx. Then Tesla, interestingly, came out with their Master Plan 3 in April, and they estimated about 46 terawatt hours of installed storage required to electrify high temperature heat delivery. The waterfall chart is a little small. I'm going to jump to it in the next slide so we can take a closer look. They estimated about 3.8 trillion of CapEx to tackle the market. And what I think is really interesting about this chart is you start with the first waterfall bar on the left, repowering the existing grid. This is global with renewables. How much, presumably, battery storage would it take? About 23 terawatt hours. But to electrify high temperature industrial heat, about 46 terawatt hours of installed storage. So a huge market potential, of course. I promise to keep this section short, talk a little bit briefly about Rondo. At its core, it sounds very simplistic, but we're developing an electric thermal energy storage system, a heat battery that is essentially a large brick toaster. We build bricks, we put them in a box, we take electricity, we heat it up with large toaster wire. It's not toaster wire, but it's just, large resistive heaters. Heat that brick up to 2,500 degrees Fahrenheit, and then blow air through it. We blow air through it just like steel blast furnaces have been doing for 200 years. This is a copper stove connected to a steel blast furnace. Hot gases come off the furnace, go through a stack of bricks, recover that heat. Fresh air then goes back through the bricks when it's time to bring fresh air back into the blast furnace, recovering that heat. So we essentially do the same thing, but slightly differently. We're heating the bricks up with wire. And then the form factor of the brick is slightly different. It's a high alumina fire brick, same kind of brick material in a different form factor. We blow air through it to recover the heat and then produce hot air or steam. To put some numbers, a typical system, we have several building blocks. We have a 100 megawatt hour unit that is going into construction right now. But ultimately, we want to be producing 300 megawatt hour units or even 1,200 megawatt hour blocks. But the 300 megawatt hour would look like this: 70 megawatts, up to 70 megawatts of input power. We don't have to use 70. We could use less, or it can ramp up and down. Store 320 megawatt hours, and then produce 20 megawatts of thermal heat around the clock. So this is the basic numbers. In terms of efficiency, from AC power in to heat out, it's about 98% efficient, which is an eye-poppingly large number, but that's being now proven in the field with our first pilot project. Of course, we've done 4 versions in the lab, and now we have a 2 megawatt hour system running at an ethanol plant in California. That's the project on the left is the ethanol plant in California. It's small. To be clear, it's just the 2 brown boxes on the left. It's not the silos. Those are grain silos for the ethanol plant storing corn. Our second unit, 100 megawatt hour unit, is starting construction right now. We just broke ground. That'll be producing steam for enhanced oil recovery in California. Right now, many oil fields in California and around the world burn natural gas to make steam to inject underground to extract more oil. In this case, we'll be building 20 megawatts of solar coupled directly to the Rondo heat battery and producing renewable steam to reduce the carbon intensity of this oil field operator's production. So let's talk about what this means for the grid, what this means to utilities, how much load could this really add? Where are we going to get the power? Is it going to be grid charging? Is it going to be from all co-located renewables? Let's start with the US target market. This is some of the work that I do. And okay, what's the total addressable market? Let's start with industrial facilities that emit more than 15,000 metric tons of CO2 per year. This is public data from EPA. This is a good starting point. For context, 15,000 metric tons, if we were assuming that's the customer is probably burning natural gas in most cases to produce those emissions, whether it's making cheese or some of these facilities are going to be pipeline compression stations that are burning natural gas. We don't have a solution for that. But for cheese and any sort of industrial process that uses heat, whether it's refineries or pulp and paper, those kind of targets, 15,000 metric tons converted to energy is about 8 average megawatts. Some of these facilities are up to 3 or 4 million metric tons alone. So there's a huge dispersion in terms of how much. But if we were to electrify everything, it would be about 356 gigawatts around the clock of industrial heat that would be needed. It's a huge number. It was very surprising to me. My background is 15 years of power generation development. I've worked 7 years for a power and gas utility. I never really thought the scope of electrification opportunity possible with industrial electrification. Now, the grid could certainly not support this. We have 1,200 gigawatts of operating generation. If we want to make this clean and not just be shifting the incremental load onto existing coal and gas units, then we need to build a lot more renewables. And assuming maybe a 30%, 40% capacity factor, back of the envelope, we need to install another 1,400, 1,500 megawatts of new renewables, doubling the capacity of the current generation system. That's just, we're talking very large load potential here and important implications for the climate. So that's one end of the spectrum. Let's talk about a specific customer, cheese production in California. This is a plant making cheese. They use about 7 megawatts of power, pretty much base load. They use about 30 megawatts equivalent of natural gas for process heat. And a couple solutions. We could design a grid-connected solution, or we could do directly connected off-grid renewables to power the Rondo heat battery. I'm going to explore both of those and what that means for electrification. But of course, the things we need, if we're grid-connected, we need low-cost power. We need less than $20 to $25 per megawatt hour power fairly consistently. At the highest level, where in the grid, where in the US would this be? Southwest Power Pool, right? Most amount of negative pricing, most amount of wind curtailment, some of the lowest prices. The chart on the right is the hub price. And in gray, we have the around the clock price. This is, again, day ahead. Real time is usually lower. And we might, in reality, be purchasing, if we're purchasing from the wholesale market, be purchasing mostly real time. But the bottom 4-hour price in red is what we look at. Things in 2018, 2019, 2020, that trend is what we would want to see if we were to charge from the grid. And we were seeing consistently probably an average of $5 per megawatt hour power for the bottom 4 hours. We can charge these systems up in as little as maybe 4 to 5 hours. So we'd be buying 4 to 5 hours of power. We're very different, completely dispatchable, flexible as to when those hours would be during the day. This is a very different load profile than most loads on the grid, very different than a data center, very different than most industrial loads. Unfortunately, most of the market rules in the Southwest Power Pool don't allow direct access. You have to work through utility under a tariff or work with that utility to craft a pass-through tariff of wholesale rates. We've seen a few examples of those kinds of tariffs, but it's not a sustainable business model to have to knock on each utility's door and negotiate a custom tariff. So the Southwest Power Pool is pretty much off limits to us right now, unless there's direct access. The market that's really the best would be ERCOT, which has some of the best rules for direct access and favorable transmission charges, where you're really only paying a coincident demand charge if you're charging when the system is peaking. Of course, we're not going to be charging when the system is peaking. So the way ERCOT is really the best market. We don't see quite as good enough prices yet in ERCOT, even in West Texas, where there's tons of wind. So, but we'll see where prices go in the future. This is what a typical layout would look like if we are grid charging for this customer. Right now, they might be using 4 or 5 megawatts of power. We would need to potentially put in up to 70 megawatts of interconnection. We don't have to have 70 megawatts. Could be charging it for more hours per day with less interconnection. A 70 megawatt new interconnection is certainly not trivial and would require that customer have sufficient transmission nearby to bring in that much power. This won't work for everybody. We would charge at about 480 megawatt hours a day typically. And then we would, in most configurations, we're looking at what we call a renewable or a combined heat and power configuration, where we produce steam off the Rondo heat battery, and then we run that through a steam turbine generator. Power is more valuable than heat, produce as much power as we can. We can usually produce about 20% of the thermal output as power. So we generate back about 95 megawatt hours, and then throw off another 365 megawatt hours of useful heat to the industrial customer. And as I mentioned, we usually need to see sub 30, if not sub $20 per megawatt hour power to make the economics work. Again, we're not consuming consistently, but switching this 480 megawatt hours per day just to an average megawatts, which is how many utilities typically think about new loads. It's 16 average megawatts of new demand per customer, and there's thousands and thousands of customers out there. But a number of challenges with this, both regulatory and access to wholesale, don't have that in many places where the power is cheap. The key point here is this is a load growth opportunity for utilities and independent power producers. The second opportunity, which I think, to be honest, is where most of our initial projects will be, and most of our projects might be in the long run, is the complexity of charging from the grid, and the regulatory barriers are such that probably most of our projects will just build dedicated, co-located, off-grid renewables that only charge the Rondo heat battery. We will most likely supplement most of these projects with a high-pressure gas boiler, so we can run that steam turbine generator 24/7 to produce base load power and heat for the customer. Many people may wonder, well, why are you aren't you trying to decarbonize? Why would you put in a high pressure natural gas boiler? Well, if we didn't do that, and there's not enough, say it's coupled with solar, and there's not enough solar happening in the wintertime, the industrial customer will be firing up their existing natural gas boiler anyway. This is a more efficient use of natural gas to produce both power and heat, and it's economically compelling as well. So this configuration represents a net loss of load to the utilities and a loss of revenue. We would love to, we're continuing to work through all of the regulatory issues, and we would love to, at the highest level, it makes a lot of sense to be able to charge from the grid to sop up extra renewables, things like that. Right now, we see more roadblocks in place for doing that, and it's going to take time. So I think in the short run, most projects that we work on will probably follow this configuration, which is a loss of load to the grid, or a reduction in load. So time will tell, but we find this to be, these opportunities are really compelling, and the market is huge, and look forward to your questions.
Right, so figuring out how the technology works. So yeah, thank you so much for being here. At Schneider Electric, we help our customers in their digitization effort through innovation and solutions. And specifically in my area of expertise, we're talking and helping our customers to build energy efficient data centers. So what I would like to do to speak and take you on this journey in the next 20 minutes to see how we and our industry is looking at the consumption of electricity, and where we see the future is going, and how we create this flexibility and what it actually means to the utility providers. First and foremost, I want to start with one word, and it's digital. When you think about, and whether we like it or not, we're living in a digital world right now, whether this is our cell phones, whether this is in industries and hospitals, hospitality, manufacturing processes, digital warehouses, everything's getting smarter. And so therefore we're creating more and more data, and somehow this data needs to be stored, processed, transported, and that consumes an enormous amount of energy. And there's actually, and this is the interesting part, and we consider ourselves right now, we're living in a golden age because there's no end in sight. It just keeps growing and growing and growing. And so it's good for our industry. And at the same time, it produces and offers a lot of challenges we're trying to help to solve. And in my role as a solution architect, so that's exactly what I do, to look and work with our customers to see how we can use technology and innovation to solve some of their business challenges. And that's what I want to talk about. So Equinix is one of the largest co-location service providers. So they said, by 2025, 90% of all the Fortune 500 companies will become digital providers. That means both selling digital services and consuming digital services. And again, that just speaks to what I said earlier. Digital, it's everywhere. It's going to continue to grow, and there's no end in sight. When we look at some different data analysis, we will project that in the next 5 years, we will see about 39 gigawatt of new capacity is required. And what I mean by gigawatt capacity, I mean the capacity, the data center capacity itself in terms of storing, processing, and transporting data will be exponentially higher. However, data centers continue to become more efficient. So we are really talking about 39 gigawatt of electrical capacity. And that represents about a 360-time increase of all the largest data centers we currently have already globally. So this is an enormous amount of electricity required. And depending on what kind of surveys and studies you read and believe in, the global energy consumption of data centers today is somewhere around 2%. Some say it's 1.5, some say it's 4. So, somewhere in that range. And it also continues to grow. We will see about a 5% CAGR over the next, 10 years. The majority of all these new capacity is actually coming online in Europe and in China, in Asia. But at the same time, in the United States, the internet giants like the Googles, the Facebooks, the Amazons, the Microsofts, and so forth. So they are really the technology leader today. And the rest of the industry is pretty much following their footsteps. And right now, a big initiative is about sustainability. How can we make data centers more sustainable? And then, 40% of all the data center capacity right now is actually in the United States. So it's the largest market globally. And therefore, even as we continue to grow, and we see it in different regions, whether it's in Virginia or West Virginia, as well in the Bay Area and other areas, Texas, the data center capacity in the United States keeps growing and growing, as I mentioned earlier. So here's an interesting thing. So this is a McKinsey study from 2023 published. So the forecast in the next 8 years or 7 years is about 10% per year. So that's a steady kind of increase. And then you see the different colors represent the different types of data centers. We see the dark blue is the hyperscalers. These are the ones I just mentioned about the Microsofts, the Amazon, the Facebooks, the Googles, and so forth. And then co-location companies, the two largest globally, it's Equinix and Digital Realty. And there's many, many others. And as you see, the light gray bar, the enterprise data centers. So these are data centers companies have on their own side. Let's say financial institution, airline industries, and so forth. So that becomes smaller and smaller and smaller as more and more services migrate towards what we call the cloud computing. So that's kind of reflected in this kind of in these kind of graphs. But at the same time, 35 gigawatts by 2030, up from 17 gigawatts in 2022. So there's a lot of growth projection, over the next decade, which we will see to happen. And that's a huge challenge because the data centers right now, and we will talk about a little later, they're becoming bigger and bigger, and power constraints is a big issue for them. Having access to affordable energy, affordable electricity. And then one thing which is not even included in this chart, we have done some internal projections at Schneider Electric that within the next decade, so we're talking here about the hyperscalers, the co-location companies, and the enterprise data centers, there is an emerging market which is called the edge data center. And the edge data center is what I define for a location closer to where the data is being generated or where the data is being consumed. So think about an industrial manufacturing facility, a smart warehouse, where the data from all these sensors, is not usable, suitable to transport it all the way to the cloud to analyze the data and then send it back. It just simply takes too long. So therefore, there's an emerging market on the edge. This is telco edges, hospitality, hospitals as well. And we project that in the next decade, all these edge, very loosely defined data centers, small, they will consume combined more electricity than all these large data centers combined. So now that's not really a big issue for us because, if I'm putting, 200 kilowatts in an industrial application as additional load to it, it's kind of minutia. It's kind of like not a big deal. But when I look at it combined, it's a massive amount, right? And somehow this electricity needs to come from somewhere. And it has to be sustainable. So that's the big issue because there's a huge driver in the industry right now to become more sustainable. The sustainability train in the data center industry has left the station and it's accelerating momentum and speed. And the question is, whether these companies are jumping on it and whether they participated. And then, of course, the question also leads to how can this be done? The large data centers, and that's the big problem, for many utility companies, they're becoming bigger and bigger. While, let's say 5 years ago, 8 years ago, by design, when somebody designed a super large data center, that was a 50 megawatt data center. Now we're seeing designs 500 plus megawatts, 200, 400, 600, So now these are massive amounts of capacity in a very specific location, campus. You see on the right-hand side, just a list, from Digital Infra Real Estate, which was published here in 2023 here in January. So the amount of data centers and the capacity in the top 10 markets in the United States. Everything is led. The largest one is Northern Virginia. Ashburn is one particular one, 2.6 gigawatts, of capacity. That was based on 2022 data. And then Dallas, Northern California, specifically the Silicon Valley. And then we see Phoenix, Chicago, Atlanta, and so forth. So as the list goes down. But the challenging part is, how can we power these data centers reliably? Because they need to operate 24/7 constantly without any interruption. And we also know that the resiliency strategy of a data center heavily relies on diesel backup generators. And that's a big topic right now. How can we green this up? And I think there we have a flexibility. So what James mentioned earlier about how can data centers just not simply become an off-taker of electricity from the utility companies, but also become a good steward in the neighborhood and potentially working closer together with the utility companies to add benefits and value, for all of them, not just as a large, power-hungry consumer of electricity. And we see in the PJM territory, specifically the Dominion zone, 20% of the power from them goes to the data center. Ireland, in Europe, we see same thing. 25% of all the electricity available in Ireland has been consumed by data centers. And Ireland says, what? We have to stop this because we don't have enough capacity for anything else other than the data centers. They welcome data centers, but they kind of say you have to bring your own power somehow. So there's a huge shift also about how data centers think about, am I just continue to become an off-taker, or how can I on-site, near-site generate electricity by myself in a certain way that allows a greater reliability, greater resiliency, more sustainability, and more affordability in terms of just simply buying power from the utility companies, which is being projected. It's not going to get cheaper, right? So I think we all agree that the power will continue to rise. And that, of course, is a big element as the data centers consume more and more of that. There's huge pressures on the data center industries. Number one, greenhouse gas emissions, and I'm not going into all the details, and I'm not quite sure other slides will be made available. Okay, so you will have it afterwards anyways. So I'm not going through and read all these details here. But greenhouse gas emission reductions, resiliency is a big, big topic, right? So, and the difference between just FYI, resiliency and reliability from a data center perspective, reliability is like everything will fail. The question is only when. Resiliency is like, okay, when it does fail, what's my strategy to kind of, overcome these challenges and continue to operate so I can provide these services to my customers. The average 5-year cost of natural disasters is $148 billion. It's an enormous amount of money of productivity loss, of revenue loss, and it's not getting better either, because every time I open the newspaper or read something online, all I'm hearing about, there's more challenges around the world, whether this is, temperature, floods, and so forth. So reliability, there's an enormous amount of cost associated with that. And then, as I mentioned, cost stability, both for natural gas prices as well as electricity prices just continue to rise. The way we look at this, there's like several priorities from the data center industry to achieve like this net zero future. That's everything they're aiming for. We want to have a net zero data center operation with all the capacity and all the electricity and energy requirements we have. So the energy, the data centers in the future need to become more sustainable. They need to continue to become more efficient. And also I want to mention, if the data center industry in the last 10 years would not have done the technology improvements they implemented to improve efficiency, we today would already consume about 4x of the energy that's being consumed today in the data centers. So with all the explosive growth in data and consumption of data and storage and transporting, because of the energy efficiency measures over the last decade, we were able to keep the data center growth rate relatively steady, like 4 to 8%. But if we would have not done the efficiency implementations, it would be a 4x of today, because the main reason is on average, over 50% of the operational expenditure of a data center is paying the utility bill. So everything that can be done to save 1 kilowatt hour, actually helps the bottom line. And to me, from a sustainability perspective, one of the elements I really focus on heavily, the greenest electron is the one we don't even need. It doesn't need to be generated, transported, switched, protected, blah, 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 the whole 9 yards. So resiliency continues to be an important part for data centers because they want to operate 24/7. And then we also see there's new emerging and nascent technologies, they're becoming available every time. And if I build a data center today, if I design a data center today, which I probably then will start putting into operation in 2024, they will operate for the next 20, 30 years until some major infrastructure upgrades will happen. So with new technologies becoming available, the question is like, how can my design I'm doing today account for technologies they may become available and may be suitable for my operation in the future? So we see that the data centers will become more customizable and more adaptive to allow for future-proof technologies to be implemented to become, again, more energy efficient, more sustainable, and improve resiliency at the same time. So we see the world of a converged energy, where the future of the worlds where gensets like diesel backup generators, UPS technologies, and microgrids are not distinct, but they're all converged and they all work together. So we briefly spoke about the interconnection queue and the challenges. That's a big challenge, right? Because if I'm generating my own power, and we talk about prosumer, so sometimes I produce, sometimes I consume, and in order to be a good steward in our communities, the interconnection is a big challenge, and that needs to be somehow resolved in order to actually work together. And without going into any details, but just for your information, so on the left-hand side, we see this is true for the last 20 years. That's a very, cartoonish like mimic how the data center design was, right? But we were the off-taker from the utility. We have some sort of uninterrupted power supply. So if something happens to the utility power, we fire up our generators on site for full capacity. So if I build a 10 megawatt data center, I have 10 megawatt of backup power sitting there, stranded capacity, not doing anything. It's like an insurance policy. Built, operated, maintained, all the kind of things, and it costs money, and it's not doing anything other than in the event something happens to the utility power. And you also see energy flowed in unidirectionally. So just from upstream downstream to the load to the actual service on the bottom, and so for cooling and all the whole things. On the right-hand side, we see a more flexible, more dynamic, more adaptive kind of architecture, where now you can see there's multiple sources of electricity, utility, on-site generation. Hydrogen is another form. It's a big topic right now in the industry. And then, we also have various kind of loads. But then you now see that you are having the ability that electricity can flow bidirectionally. So it's not just simply anymore a downstream from the utility, but if we produce more than we need at a certain point in time, we can actually export. One of the largest microgrids we at Schneider Electric have done in a commercial setting is actually a mission critical facility, but it's not a data center. It's at the Naval Air Station down in Miramar in San Diego. And so they have a big microgrid, and their mission is, of course, their mission is to protect the country, but from an operations perspective, they need to be autonomous for 21 consecutive days. So if something happens to the infrastructure externally, they need to be able to continue their mission for 21 days. And then a few years ago, when there was a huge heat wave in Southern California and the utility companies, SD, G&E, had to institute rolling blackouts, they were asking if they can contribute. So although it was initially not designed, this microgrid, to do that, but they were able to produce sustainable power and export it back into the grid to help neighboring communities, right? So when you think about from a residential perspective and from a health perspective, so there's people on ventilators and other kind of, critical applications. And now all of a sudden, instead of having no power, now the microgrid, the on-site sustainable power generation was able to support the community. And we clearly see that this is also a role and responsibility for the data center industry. And especially when you think about you having a 200 or 500 megawatt facility sitting there, and now they have these assets which otherwise would be stranded, they can actually use it, to support the grid. So that's why the interconnection is becoming a critical component in all of this. And without going into all the details here, but companies, data centers, looking at all these different kind of driven or customer-driven choices about on-site power generation, gensets, batteries, fuel cells, flow batteries, renewables. And as we all know, data centers is one of the largest power dense industrial application compared to office buildings and other industries. So photovoltaic, as good as it sounds, but you need 4 or 5, 4 acres for a megawatt. And if I have a 500 megawatt facility, you can imagine how much more land I need adjacent somehow, and to produce the equivalent amount of electricity when the sun is shining. Another topic which is getting into the forefront of many data center customers now is SMRs, small modular reactors. And just about 3 weeks ago, I had a conference session, and we talked about the specifics about SMRs for the data center industry. And so we definitely, it appears, let's put it this way, I don't have a crystal ball, but it appears to be that we will see by the end of the decade, we will see an SMR or multiple SMRs implemented on site directly on the data center side. So it could be load defection to a certain degree, but data centers somehow, they're looking for greater resiliency, and they will do anything they can if it's cost affordable and from a legislation, from a regulator's perspective, from a safety perspective, to actually make this happen. So in places like Northern Virginia, where we have massive amount of electricity required, one could easily ask themselves, so why do we not put SMRs in there directly, very adjacent, close by? And then we have sustainable, renewable, reliable on-site generation, which of course, don't get me wrong, opens a whole nother set of cans of worms, is it possible, when, how, what are we going to do with the waste, and blah, 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 right? But that's the idea. And then similar to what I just saw about the, was it the hydrogen 24/7? So the data center industry also, these large off-takers, they buy all these renewable energy credits, whether this is virtual power purchase agreements or PPAs on an annual basis. So if I consume X amount of gigawatt hours a year, I'm buying the same one, from renewable, so I can communicate to my customers, who use my data center capacity, or whether I'm a Google or a Facebook, whatever, hey, I'm 100% green. Well, that's on an annualized basis. Now, the industry and the Googles and others, are really shifting towards a 24/7 carbon neutral operation all the time, not just on an annual basis. And that causes a new challenge So we see that these virtual microgrids, with on-site and near-site power generation, actually will be able to facilitate that, including load shifting, what they do. But ultimately, it's all about using multiple distributed energy resources in order to be able to accommodate a 24/7 carbon free data center operation. And then I thought, just since hydrogen is also a big conversation in the data center industry, and I find this interesting what I saw earlier today. So we're looking at the round trip efficiency, right? And you mentioned about the heat battery. I like this actually. I've learned a lot already. Thank you so much for that. With an efficiency of like, what did you say, 98 or 89%, but pretty high. So pretty high. So when I look at, gas is of course also considered for like backup generation, so forth. So when I look at this, I have a 50% efficiency, for natural gas, and then steam reforming, and then using hydrogen. We just talked about earlier about it. So you guys are way more experts than I am. But traditionally, when I look at it, the third row, buying the electricity from utility companies is actually pretty efficient. Right? I mean, yes, I have my transmission and distribution losses and so forth, but it's somewhere around, whatever, give and take 80, 90%. So that's pretty good in comparison to the alternatives. However, because of the sustainability aspects and the becoming more flexible and adaptive and more in control of your own destiny, the idea of using hydrogen, and Microsoft is pushing the envelope really hard, and they've done last year a 3 megawatt demonstration process, where they produce hydrogen through electrolysis and then power a data center, and they're going to continue in this effort. But here we are somewhere around between 25 and 30% of efficiency. And this is one of the questions I had for you, because you talked a lot about using electrolyzers to generate hydrogen, but what about fuel cells to actually use this hydrogen? Because the data center industry sees hydrogen as an energy storage method, right? So I'm producing, maybe I use it for my fleets and other kind of operations, but I'm also storing it. So in terms of need, in terms of energy arbitrage, when electricity prices are high, then to self-generate in order to reduce my operational expenditure. So that's the whole idea. Although the efficiency is not as advantageous as perhaps other technologies, that's I think why also people look at SMRs, as an opportunity, because there's a nice match between the electricity an SMR is capable of producing and the amount of electricity I need in the data center. While if I have hydrogen, I still need to store it. And there were like these physical dimension comparison in terms of like, hey, if I have a 100 megawatt data center and I want to run 24 hours or 48 hours autonomously on my hydrogen, these huge spheres I need to store on-site hydrogen. So that's a big challenge, right? So therefore, form factor, of course, cost of land and so forth is always an issue as well. All right, so I think the key takeaways, so the data center capacity will continue to grow, and that's true for both the hyperscalers as well as what I just mentioned earlier, the edge data centers and edge compute power locations everywhere, although less of a challenge. And then the data centers are looking for ways to become more autonomous from the utility companies and also becoming prosumers. Sometimes produce electricity, sometimes consume it, and work closer together with the utility companies. And then 24/7 sustainability energy matching will be kind of like the holy grail for the data center, and the efforts are currently already well underway, and we will see more to come. And with that, I think that's it, and I really appreciate it. Thanks, guys.
All right, thank you, Carsten. And one of the numbers that I'm walking away with is 500 megawatts of a data center. And if it was inefficient, right, that would have been the equivalent of 2,000 megawatts in a very dense location, and the implications of that. But then how that would work with being autonomous and how much the grid would actually see of that load. And so things I think that we can get into as we have the question and answer section. So Agee is going to round up this discussion, because everything that these folks have been talking about, he has to deal with at the very end of the day. And so I want to hear his perspective from ERCOT, and Texas, of course, has been name checked a couple of times during this discussion already. And so please welcome Agee to the floor here as he gives his discussion on the ERCOT perspective.
Thanks, and yeah, appreciate the shout outs earlier in the discussion. So hello again, my name is Agee Springer. I'm the manager of large flexible load interconnection at ERCOT. For this panel, I'm going to be talking about integrating some of the large loads that have been discussed while also maintaining grid reliability. So I'll provide a little bit of an overview again of the types of large loads we're seeing. And then I'm going to be talking a bit about the interim interconnection process that we put together to handle some of these faster to interconnect large loads. And then finally round it out talking about our challenges with load forecasting. And so, yesterday my talk was very much on the operational side. This will focus much more looking out into the future. So I showed the slide yesterday. It gives kind of an overview of the large loads that we're seeing come to ERCOT. If we kind of look at them from the lens of how long do they take to interconnect with the grid, and also how sensitive are they to price. The historical large loads have typically been 3 to 5 years minimum to interconnect, and then also generally not very price sensitive. But now we're seeing, these newer types of large loads, so crypto mining, data centers, oil field electrification, and in the future, hydrogen, that are going to likely be faster to interconnect in some cases, and more price flexible. So, if we kind of look 5 to 10 years out, we really expect to see kind of all 4 quadrants of this graph filled. And, I think you heard that from some of the other panelists that, a lot of these technologies are coming. These, sort of 2 features of these large loads present kind of distinct problems for grid reliability. The first is that short timeline to interconnect is really faster than our existing planning processes were designed for. And I kind of glossed over that yesterday, but as promised, we're going to circle back to it in this talk. The sensitivity to price also, I talked about the operational challenges that presented yesterday, but from this talk, we're going to focus much more on the impact on load forecasting and how it makes it much harder to kind of predict what the overall impact both to our peak load is going to be and to some of our resource adequacy and capacity needs. Before jumping in on the details, though, this is a more detailed look at the sort of high-level 42 gigawatt number I presented yesterday, which is just the amount of loads that have a short timeline to interconnect. So, again, faster than those existing planning processes. This is an overview of what we're tracking. And the 42 gigawatts is really comes with a bunch of caveats. The first is, we have a number of projects that provided basically nothing more than a location they want to interconnect in a megawatt amount. They haven't even provided any interconnect studies or anything to make us think they're real, and including a date. And so those kind of all go into that 2027 bucket. There's also a number of projects that have moved through this interconnect process and had some of their megawatts approved for interconnection, but not all due to reliability limitations. And those, we're still in a lot of cases waiting for indications from the customer about whether or not they want to wait for transmission upgrades to connect the rest of the load. And so those all kind of get lumped into 2027 until we know what the customer wants to do. So that gives us kind of the worst possible scale. But really, if you focus in on the 2023 bar, I think that's really maybe a better look at what we're expecting. So, there's 2,600 megawatts that are approved to energize now. They've already gone through reliability review. They're approved to energize. Another 4,300 have had their planning studies approved, but haven't yet been modeled or moved into the production systems to get approved to energize. And then there's another 8 gigawatts that are kind of under active review. And I think that's a better indication of the scale of what we're kind of expecting in the near term, is somewhere between, let's say, like 8 and 15 gigawatts of large load. Now, remember, the peak load of the ERCOT system is 80,000 megawatts. So that's still a really significant amount of large load that's coming. But I just wanted to kind of show the graph because it also highlights a lot of the uncertainty that we're seeing. It could be as little as 5 gigawatts, but it could also be as much as 40, and that's a pretty big range when you're trying to plan and to forecast. So I'm going to focus in now on these short timeline to interconnect loads and talk about how we're addressing them in the planning time horizon. As I mentioned, this short timeline to interconnect is really faster than our existing regional planning group, regional transmission plan processes were designed to handle. And it's definitely faster than any transmission upgrades could be built unless those upgrades were already approved and under construction, for other justifications. And those things kind of combine to, say, okay, well, we don't really have a good process right now to ensure that these interconnections are actually reliable for grid stability. So ERCOT established in March of 2022 an interim interconnect process to kind of govern the interconnection of these large loads. A couple points I want to make before I talk about how it actually works. The first is that the need for this interconnect process was driven entirely by the speed at which these loads want to connect to the grid. It has nothing to do with their flexibility. If Dow Chemical came to us and said, we want to build a new facility in 12 months and it's not going to be flexible at all, it would still have to go through this process. So it's really just the speed to interconnect that's driving the need for this. It's also driven by, or I should say, it also doesn't add any new interconnection requirements in terms of what has to be looked at. It's really more there to ensure that the existing ERCOT and NERC obligations are being fulfilled. And again, that ERCOT is meeting its reliability obligations to the system as a whole. So who has to go through it? It's basically the loads we've defined as being large loads that I talked about yesterday. So any new load that is 75 megawatts or greater, or an increase of an existing load of 75 or greater within 2 years has to go through. If it's co-located with a generation resource, that number drops to 20 megawatts. And again, that's just because it's a material modification of the generation resource. There's also a caveat if it hasn't been studied in any existing process, which now this process has existed for about 15 months. So there's no loads going through that were studied in an earlier process. Anything coming in now is going through this interim process. The process itself is, basically 3 phases. The first is ERCOT review of required interconnection studies. So just with all our other planning processes, the transmission service provider is the one that has the direct relationship with the customer. So the TSP performs the reliability studies, identifies the transmission upgrades that would be required to serve the full requested load. What is new is that those studies then come to ERCOT for review. And ERCOT is going to be looking at the system along with approved transmission upgrades that are already in process to determine how much load can actually be served while meeting reliability requirements by the customer's interconnection date. Remember, it's within 2 years, so this is faster than any new transmission could be studied, approved, built. So ERCOT is there to ensure that we basically figure out how much load could actually be reliably interconnected when the customer wants to come online. And ERCOT sets a limit based on the reliability criteria that remains in place for the customer until new transmission is actually built. Once the limit has been set, then the customer is able to get into the operations models, the future planning models, and then once it's in those models, then it can move through the approval to energize process where the telemetry is validated, the modeling is validated, and then it's approved to begin consuming energy. So, it's actually the later stages are basically identical to our other planning processes. It's really that first step that is new and again, driven by the fast timeline to interconnect. Now, even though those processes existed for about 15 months, it's still relatively new. And because it's interim, it also has a lot of limitations. A few of the big challenges, tracking of load ramping schedules, very ad hoc. There is not only driven by the customer actually getting their load equipment on the ground and energized, but also a lot of times there's load increases that are conditioned on a transmission upgrade coming into service. So we may have a customer that wanted 300 megawatts and we say, okay, well, you can have 150 now, but there's already a transmission line under construction that would allow you to get to 220. And then we have to track, and the TSP has to track when that upgrade actually comes in before we allow the load to consume more. So there's no standardized way of doing that right now. Each TSP has kind of different methodology. So it's a very kind of fluid situation that will be addressed with more formal rules probably later this summer. There's also a sort of a natural transition between the interim process, which is kind of 2 years or less, and longer term growth of the load, which would be handled under existing planning processes. And the customer may have a projection of load growth that kind of spans both time periods. And so the question has kind of come up, well, how do we draw the line between what is governed by that interim process versus what is going to be handled in the longer term traditional planning processes? So that's still being defined. There's also no interconnection fee right now because this is an interim process not governed by ERCOT protocols. We can't charge a fee for the work that we're doing. So it kind of leads to a lot of duplicate and frivolous requests in our queue. See that 2027 bar on the graph. There's also one other big topic that's come up in this panel and also some of the panels yesterday that I didn't put on my slides, but it's worth talking about, and that is transmission upgrades. There is, for a lot of these customers, the project is not really viable unless the transmission can actually support it. And our existing processes really justify transmission upgrades based on load that's already signed agreements to interconnect. So we have a little bit of a chicken and egg problem. There's also a lot of concern that some of these customers, especially the crypto miners, may not be there in a few years. And there's a real question of, well, should we be building transmission for flexible loads? And are we at risk of building transmission that's not going to be needed in a few years? And so, especially because these loads are coming so fast and may be gone by the time we actually build the transmission, that's a concern as well. So, just to kind of tie it back to some of the other topics we talked about. This panel has focused on industrial customers that tend to have longer timelines to interconnect. And so, of course, the question comes, what about like hydrogen and some of these other large industrials that are further out in the future and how fast they want to come on the grid? Those are going to continue, at least for the time being, to be addressed through the regional planning group process. What is probably going to be different is that because of the size of the loads and their ability to throw the grid around that I talked about yesterday, we probably will look for additional registration data from them to kind of aid in load forecasting, which takes me to load forecasting. So I'm going to start talking by throwing up a slide that I had yesterday, and I promised I'd come back to it. And I think some of the other talks have really illustrated a lot of the uncertainty in what's actually going to be built, what the needs are, what the flexibility is. And that's exactly what we're seeing as well. There's a lot of information that we really don't have good visibility into, even a year and a half into this, really addressing these flexible loads. So both in the interconnection phase and in operations, we have a lot of question marks still, and that makes forecasting really challenging. If I had to kind of really describe for large loads, the big challenges we're seeing, it's sort of two buckets. The first is the growth of the load is really hard to predict, and it's sort of compounded by the fact that the load is flexible. So what is its contribution to peak? That's hard to predict. The behavior of the load is also hard to predict. When is it going to be flexible? The question marks we have really kind of feed into that. So for the growth topic, one of the big things we're seeing is that the load itself is actually lagging from when we approve it. So we may approve, I mentioned the 2,600 megawatts of approved load. The actual consumption we've observed is only about 2,000 megawatts. So there's a lag from when we approve it to when that load actually shows up. And that's, I think, driven mainly by the fact that most of it's Bitcoin and data centers right now. So those loads are really modular. The vast majority of the consumption is driven by either the mining equipment or the servers that are actually installed. And, we're seeing that a lot of these customers aren't actually buying those equipment until they actually know they can interconnect. So, for forecasting, we could potentially look at the supply chain, especially for Bitcoin rigs. There's really only two main suppliers, and potentially look at what's actually being bought up to kind of predict the load growth. And the problem is we still don't have good visibility into which customers are buying what equipment and what share of the supply they're getting. So, that really remains a challenge. And as the type of load diversifies, that's not even really a viable approach anyway. When we look at behavior, again, right now, it seems like it could be simple. It's, mainly crypto mining. And so at a surface level, if we look at, okay, the economics behind that, how much Bitcoin is awarded when they mine a block, what the price of that Bitcoin is in dollars, transaction fees, how hard is it to mine a Bitcoin? And, then also what equipment are they using to do it? How efficient it is? We could probably back into a rough strike price of where that mining activity becomes uneconomical. And actually we have one of my colleagues at ERCOT has actually done that for a couple of the common miners. So, we at least have kind of an idea of a range. And so in theory, if we understand that, then we kind of, we could potentially use that in a, machine learning algorithm and along with the historical load data to kind of project what the likely behavior of these Bitcoin loads would be in our load forecasts. And we could probably do something similar for other flexible load types like hydrogen. The problem is that there's way more nuance at a site level. So, for the Bitcoin and the data centers, they have third-party hosting agreements where they provide, essentially some of their capacity. They're providing a roof and the electricity hookup to other miners, and those agreements may have terms that we don't know in terms of guaranteed uptime or situations where they have to curtail. So some of the load on site is not even really theirs, and we don't know what that's going to be doing. There's structures in their PPAs or their interconnect agreements that may change the incentives for flexibility and flexible behavior. And we've also been looking more at temperature-driven curtailment. So especially for the air-cooled data centers and Bitcoin mines, there potentially is a temperature effect where they may choose to either underclock or overclock their processors to gain efficiency or to gain speed. And that affects also, how much energy they're consuming. So lots of different kind of nuances make it really challenging to forecast these loads. This is just a quick overview of how we're forecasting them right now. ERCOT's 2022 long-term load forecast projected about 700 megawatts of growth in large flexible loads. That would get us to about 5,000 by 2027. I think from the chart I showed earlier, that is likely an underestimate, potentially a significant underestimate, and I expect it'll be revised this year. What we're considering the contribution to peak demand is about 10% of their total demand based on what we observed last summer. So we do see a lot of curtailment on the worst days, but even then there's still some loads that either choose not to curtail for, likely their PPA structure, or there is just some base load that is just not flexible. Generally that's cooling, and other sort of, they can't really get down to zero in a lot of cases. I expect that will also be revised this summer. We're expecting a lot more mining load to be on the system this summer compared to last summer. We should get better data. And so I expect, kind of all the numbers on this slide will be updated later this year with the long-term forecast. I'll also make the same plug I made yesterday, which is having more data is good, but having registration and participation in the market as controllable load resources is better, because then we are provided with a lot more data on the incentives that drive flexibility. And that I think is going to help us, in addition to the operational benefits, I think it helps us with forecasting as well. For the short-term load forecast, at the moment, ERCOT is not making any explicit adjustments for large flexible loads. The number in operation was much smaller last summer. We are in the early stages of an initiative to generate an LFL-specific forecast that would look at the next 168 hours. And I should add also our existing model probably is picking up some of the flexible behavior, just looking at the historical inputs it's getting. But an explicit forecast would help. And again, the more that are registered as controllable loads, the better our data is, the better our forecasting is going to be. So that gives kind of an overview. I think maybe my biggest takeaway is just there's a lot of uncertainty right now, and it kind of exists at sort of every phase of from interconnection all the way through operation, and so that makes forecasting challenging. But certainly it's changing, and the industry is changing, and there's a lot of new loads showing up. So Hopefully we'll talk about that more in the Q&A. So thank you.